Dear laureates, presidents of the Swedish Academy of Sciences and the Crafoord Foundations, ladies and gentlemen, we're all here because of one person, Holger Crafoord, industrialist, visionary, and donator. He was not born with a silver spoon in his mouth, as we say in Sweden. Instead, his single mother had to work hard to bring him through school and to give him a chance to study at Handelshögskolan in Stockholm. And there he was recruited by the industrialist Ruben Rausing, which is fairly famous, at least in Lund, to work with him here in Lund. And jointly they founded Tetra Pak, as you can see, with this beautiful mathematical form for cream in this case. But this was a worldwide success and is now a multinational company. But that was not enough for Holger. Together with Nils Alvall, he started to develop and produce the first clinically useful dialysis machine, the artificial kidney, and which has saved millions of lives during the years. The artificial kidney was invented by Professor Nils Alfors. You can see here with Holger, and I think that is one of the first machines, probably. But that was also not enough for Holger. Making so much money on science, he wanted to pay back, so he founded the Crafoord Foundation, which is funding a lot of research in southern Sweden, especially Lund, both small grants and big grants. Here you can see Holger Crafoord's daughter carefully inspect a machine. Really careful. Well, I will also be careful in look. Maybe it's like a robot surgery machine, which could go wrong. But also big donations to, for example, building Holger Crafoord Center of Economics, not far from here, Center for Language and Literature, and Lucus Medicus Lunensis. As you can see from the name, that is now a student place, but it was actually Holger's home originally. And last but not least, the Crafoord Prize. And as a mathematician, I look back with nostalgia to the last time we handed out the mathematics prize. You can see here Professor Jakob Eliashberg in 2016 receiving the prize from His Majesty the King. Thank you very much. Thank you.
Crafoord Laureates, presidents of the Royal Academy of Science and the Crafoord Foundation, ladies and gentlemen. So it's an honor to present the work of Professor Bombieri. So let me start then with the prize motivation for outstanding and influential contributions in all the major areas of mathematics, particularly number theory, analysis, and algebraic geometry. I should say here that it's almost impossible to summarize everything that Bombieri has done in one sentence, so we could have mentioned minimal surfaces, for instance, but I mean, it had to be one sentence. So let me then give you a short CV or Lebenslauf. So Bombieri was born in 1940 in Milan, and I mean, he was a mathematical prodigy, certainly. I think at 8 he read his first textbook in algebra. And then at 15 he came across a very famous book in number theory, and that became maybe his greatest passion. So already at 16 he published his first scientific paper, and then he wrote other papers already as a teenager, which is very rare. And then, of course, he came into contact with leading mathematicians, and especially then Giovanni Ricci became his supervisor in Milano. But since his greatest passion was in number theory, there were not so many number theorists apart from him in Italy, so he also spent 1 year later in England for Davenport, and that I think was very fruitful. And he became professor very early, when he was 63 in Cagliari, and then in Pisa, and 45 years ago then he went to Princeton at Institute of Advanced Studies. And with 175 publications and 3,400 citations, it's clear that he has been very influential. So it's not surprising then that he had already had some other prizes before this. So I have made here a list. I don't think it's a complete. Let me single out particular then the Fields Medal, because that is the highest distinction that a mathematician can get, and it's much more difficult to get a Nobel Prize because you can only have it each 4th year. But even then, in one of the report, he was not described as a Fields Medalist, but as a Super Fields Medalist. So there's apparently a classification among them. He's also not just, he's a member of our Royal Society, but he's also a member, of course, of other, like the National Academy of Science and Académie des Sciences and so on. So next, then I would like to say something about his mathematical contributions. And as I said, he started as a teenager with number theory. And if you look at the last 20, 30 years, I mean, it's clear that number theory dominates. But even within number theory, he has done different branches of number theory, and he's an expert in both Diophantine problems like related to defined approximation and transcendent theory, and in analytic number theory, especially then distribution of primes, and he invented new techniques with sieves, and I think he will say something about that here or tomorrow. In Italy, there is also great tradition both in analysis and geometry. For instance, in algebraic geometry, Italy has dominated for almost 100 years. So he had really fulfilled this tradition and worked in several different areas. So I come from Göteborg, and where we have a strong group in complex analysis in several variables. We have then been influenced by Bombieri, where he extended these L2 techniques of Hermander. But even then, although he doesn't have so many papers in algebra, I think that was a paper that impressed me most of all. So I first heard of it when I was a graduate student in Stockholm, and Serre came, a famous mathematician, and at that time there was a big project. They tried to classify all finite simple groups, but they were stuck. I mean, they were really brilliant people, and they couldn't solve it. The one problem was extremely hard. But then Bombieri, who worked with completely different mathematics, looked at it and he solved it. And I found it absolutely unbelievable when I saw that. Then, of course, you find his name in textbooks: Bombieri-Length conjecture, Bombieri norm, Bombieri-Vinogradov theorem, and so on. And when I think about these 4 areas of mathematics, I associate to Euler's identity. Euler, he was the greatest mathematician in the 18th century, and he managed to unify 4 numbers in one identity, and they all represent different areas of mathematics. So what's unique with Bombieri is that he has solved problems in all these 4 areas, because nowadays mathematics is gigantic, so it's very rare that someone is a strong analyst and a strong algebraist at the same time. So that, I think, is very characteristic of Bombieri. So this was formulated very well when he was nominated to the National Academy of Science, so I would like to quote that. So, Bombieri is one of the world's most versatile and distinguished mathematicians. He has significantly influenced number theory, algebraic geometry, partial differential equations, several complex variables, and the theory of finite groups. His remarkable technical strengths is complemented by an unerring instinct for the crucial problems in key areas of mathematics. So maybe let me just here also focus on these technical strengths, because of course you need to have good ideas, but in mathematics you really need to carry them out as well. And this often involves very long, complicated computations, and Enrico, he's a master on that, really. So I had a position, teaching position 6 years at the ETH, University of Technology in Zurich, and then I assisted at lectures of Bombieri, which was really interesting. So lectures about the Diophantine geometry, and one of my colleagues, he took notes, and this later became a book, which is really an outstanding, one of the best books I have, and you can see here what are the criteria so to receive this Joseph Doe Prize. So and he has also written other books in other areas, but I think this is really a masterpiece. So there is also La Grande Finale. It's really his own proof of a famous conjecture by Mordell. So it's really one of the best books I have. I don't know that much about Bombieri's private life, but I know that he has many other interests. So when I was invited to Princeton in 2010, then he showed me a painting, and then I learned that apparently he carried paints and brushes with him when he traveled. So and one of his best paintings is apparently a match between Kasparov and this chess computer Deep Blue. So I've not seen it, but I would like to. So Bombieri, of course, as many other mathematicians, have played chess, and I don't know much more. I've heard that he's good at cooking and he likes poetry and so on, but I don't know. So please let me instead show you the town where he come from, so give you a travel tip. So this is a University Cloister of Milan, so maybe there is something for you now if you want to for your holidays. So I think that's all I wanted to say. So I now please ask Professor Bombieri to come to the podium and give his lecture. So.
Okay. How do I start? Oh, there it is. Next, yeah. So the title of my lecture is 2000 Years of Prime Numbers. Strictly speaking, it should be 20,000 years of prime numbers, but 2000 is a round number. So, the origin of mathematics came with the mathematical operation, sum and the inverse, which means difference, is rooted in simple counting, such as the number of sheep in a flock, quickly evolving in its use in commerce. Counting base 10 is done today because we have 10 fingers. And computers use base 2, which is the simplest, and in a way, which is the most efficient. So computers started actually with base 10, and then they figured out that base 2 was much better. Base 12 was used for commerce, and still have a carton of dozen eggs, which we buy at the supermarket. I don't know if this is so in Sweden, but certainly in New Jersey it's like that, in Italy it's like that. And the original multiplication goes back to the need of measuring land. And so again, this mathematical operation were useful in the formation of society. So number theory starts with two simple operations, sum and product. And then the inverse, difference and division. Of course, you cannot divide two numbers exactly, unless special cases. So what you have a quotient, an integer, and then a remainder. And the numbers that have no divisor, except one, of course, and those are the prime numbers. So the sequence of prime numbers 2, 3, 5, 7, 11, and the sequence of primes does not stop. This requires a proof, and the Euclid argument, which was around 330 BC, consists the observation that if there are only finitely many prime numbers, take the product at 1, you get a number which has to be a product of primes, so some new prime has to come up. Whether this argument was known to the Chinese before, I'm not sure. Probably they did, but I did not find a precise statement for which manuscripts contain that. So unique factorization also was known. And in modern times, we come to the mathematician Euler, a true giant that founded modern mathematics. So, entered university at the age of 14. He did his studies in theology, but he was a mathematician. And so the mathematician Bernoulli convinced his father to let him do mathematics, and this was a fantastic thing for mathematics. So Euler went to Basel, and they had 13 children, but at the time, most of them died very early. And some of his great mathematical discoveries were done when he was holding a baby in his arms. And then went to St. Petersburg, 76, at the age of 59. And half of his work was done when he was blind. Absolutely unique thing. And if you look at Euler's works, it's 50 volumes. It's not, it's a fantastic thing. His correspondence is also fantastic. You have to read it if you have time. And he has a little booklet against what today the crooks, they think they have done mathematics, but it's not. So, and the zeta function, which is the most famous function number theory, appeared in Euler equation. In the sum of the reciprocal of the squares is pi squared over 6, and Bernoulli found it very strange. And the factorization of the negative powers of the integers, the sum of the negative powers of the integers, as an infinite product involving prime numbers, is the analytic form of the uniqueness of factorization of integers as a product of primes. And even today is the foundation of the study of primes using analysis. And Euler also tried to compute, he knew the sum of zeta 2, for example, pi squared over 6, but somehow tried zeta 3 for years and years, and say he tried forever to find it, but he could not reduce to numbers, logarithms, and or pi or things like that. So it represented, Euler thought it represented new type of number. So it found the relation between the logarithm and the sum of the alternating sum of reciprocal of integers, and so on, introduced what are called today the multiple zeta functions, some involving products of negative powers of integers, and discovering that people are still studying those things today. They appear in those new numbers in many constant mathematics and physics too. So the problem in understanding relation with multiple sums remains a great interest, and zeta 3, zeta 2, zeta 4, Euler noticed the could compute exactly in terms of powers of the number pi, but zeta 3 he could not control, and the first time to prove that zeta 3 is not a rational number was only in 1979. And it's not known yet if it is transcendental or not, but certainly it is. Euler noticed the sum of the reciprocal of primes is divergent. And here is a formula which is found in one of the books of Euler's. And this is essentially the functional equation of the zeta function. It was using alternating sums rather than sum with the plus, because the sums are convergent, or at least could be even a special number. And so this is the first example calculation, what is called today the functional equation of the Riemann zeta function. Pi of x is the number of primes up to x. Legendre observed it's a good approximation in the range of tables, and this strange number was obtained by using the method of least square deviation, which was used in probability theory at the time, and used also by astronomers in studying the motion of planets. If you have numerical data of the same thing, but they're all a little different, so this least square deviation is a classical method today in probability theory. Dirichlet came from the Belgian town of Richelais, so one should say Dirichlet, but today it's becoming Dirichlet. And the young man from Richelais, his father was postmaster. At the age of 12, he was already in the local university, and he started mathematics very early. And Dirichlet stated what is today the prime number theorem. He thought he had a proof, but the proof had to wait a long time. So even he was hoping to have a proof, but his proof certainly was not valid. And Dirichlet observed that the number of primes up to x is not about x over log x. It's given by the sum of the reciprocal of the logarithm when n up to x. That's a much better approximation. And this was found by Kronecker as a comment in Dirichlet handwriting in the offspring belonging to Gauss. So this little piece of history was rediscovered relatively recently. And finally, 1850, the Russian mathematician Chebyshev gave a correct proof of the order of how many primes there are up to x. It's about x over log x. The actual number is still very complicated to study. So there's a Dirichlet series in which sum of the reciprocal of the integers to a power s, but the character is 1 or -1. The character product is product of characters, it's periodic, And then as a special equation relating the value at 1 minus s to the value at s. Yet if complex carry this complex number, you have to also go to the conjugate. So this was essential to study the number in progressions. So Qn plus a when n equals 0, 1, 2, 3, and so on. And so to prove for infinitely many primes in a progression took a long time, and because you have to show that corresponding zeta function, so L function, is not 0 when the value is 1, the variable is 1. And he said he was able to find a solution. It was in Rome, in the Sistine Chapel for the Easter celebration. So, you know, these mathematicians, they go around always thinking about their numbers, their theories, and so on. I do the same too. Not as well as they did, but okay, it's a kind. So, in 1859 was the big revolution. Riemann studied the Euler series in a variant as a function of a complex number, and found an equation relating value of zeta s to zeta 1 minus s, and which, by the way, the equation for when you take the alternating sums of the powers was already studied by Euler. But Riemann understood that this was more fundamental than the sum with alternating signs. Anyway, Riemann theorem was a really astonishing thing. An exact counting of primes up to a given number in terms of the solutions of the function zeta, now called the Riemann zeta function, when s is a complex number. And then, in terms of these complex numbers, it found the exact formula for, well, the formula involving the pi x is number of primes up to x, and this is what he proved. And then from there, with some manipulation, you can isolate pi x by itself, which I will not do here. So Riemann showed how to isolate things in terms before, and then so Riemann noticed that usually the number of primes up to x is less than the integral of 1 over log of x. Is not and observed that up to 1,000,000 pi of x is less than the logarithm integral of x. Now everybody will think that's good numerical evidence. Well, the first sign change is around 1.398 times 10 to the power 316. No one knows exactly the number, but this is almost certain that the first sign change is like that. So talk about numerical evidence, about being positive, the difference, the sign change, after 10 to followed by 316 zeros. It's amazing that such a thing happens at all. So I'd like to say just a word very quick about Riemann paper, which contain a constant minus log 2, which is given in Riemann manuscript as log of psi 0, which is wrong. This was corrected by Ginocchi in 1861, but French Academy paid no attention to that, saying that this was a lapsum calami for log psi 0, which is also wrong. So at the time we create our idols. Riemann was one of the idols. He could not say anything wrong, so they say something wrong to correct the point. And this happens again and again. So be careful in what you hear. So there's a notebook by Riemann, and Riemann conjectured that in every case he was to compute the zeta s, when s is a complex number, a real part 1/2. And this is the Riemann hypothesis, which today nobody knows how to prove. Now, one exception will destroy the distribution of prime numbers, just one exception. And it's been verified for billions, I don't know how many first solutions of the equation, and it's certainly correct, and nobody knows how to prove it. One is the biggest open problem in number theory. Now, if you solve it, you get $1 million. The result, the foundation receives every year hundreds of papers, wrong papers by people claiming to have solved Riemann hypothesis. So you mentioned about the failed attempt of many professionals and also amateur mathematicians. The work of amateurs is characterized by denial of failure. That's an old problem. The Pietro Ferroni, mathematician at the court of Grand Duke of Tuscany, wrote in 1790, "The lesser men always defend their own mistakes in the harshest possible way, and in doing so they right another 100 errors." Still true today. So I don't know if you ever came across such things, but any professional mathematician has seen this again and again. So, story about Riemann's notebook. I learned that from André Weil. Hilbert again admired Riemann's intuition depth, and he used to say, Riemann's always did his work only with deep, original, profound, abstract ideas. Well, a long time ago, André Weil went to Göttingen to meet the Siegel. Started talking about Riemann, and Weil asked to see Riemann's notebook. Notebook arrived, and they opened it, and some was written in loose sheets, fell on the floor. This is an example of Riemann. Siegel picked up one of these pages, showed to Weil. Well, I don't know if I have a picture here or that. No, apparently not. Anyway, it was the page filled in every direction with numerical calculations and no words. And Siegel said, well, this is an example of Riemann's deep abstract thought. Of course, Riemann had deep abstract thought, but those were, the foundation of that was hard calculations, numerical evidence, not just abstract. There was also something to support that, and then the abstraction comes as a result of not just great intuition, but also the collection of evidence. So there's a word about work of amateurs by Pietro Ferroni, mathematician at the court of the Grand Duke, wrote in 1970, the lesser men always defend their own mistakes in the harshest possible way, and in doing so, they right another 100 errors. Still true today. And so André and Weil went to Göttingen with Good and Siegel, And Weil asked to see Riemann's notebook. So the notebook arrived, and somehow the package broke, and all the sheets went on the floor and were showed to one of them, gave to Weil, say, this is an example of Riemann deep abstract thought. I don't know if a page, but it was a page full of numerical calculation all over, sums and so on. They were a calculation of the solution of the Riemann equation, numerical. But so eventually the prime number theorem was proved, and the Mitter-Leffler, that name should be familiar to Swedish mathematicians, was interested in promoting mathematics in Sweden, and there is interesting correspondence between Mitter-Leffler and Stilsius about Riemann's paper. And some of this has been published, but I had the chance of looking at the archives, and there are many other things in these letters which have to be really examined, and not only with Riemann, but this archive of the correspondence of Mitter-Leffler is historically extremely important. Okay. So the Riemann hypothesis remains the greatest open problem in number theory. One exception, the whole thing collapses. And has been verified now for, I forgot the first many million zeros solutions. Is certainly true. And there is a similar structure in so-called finite fields, so the zeta functions of finite fields. And the analog Riemann hypothesis is a very famous theorem which had lots and lots of application in number theory, and is true. But the classical Riemann hypothesis remains the greatest open problem. So let's see. Let's skip this one. So the mathematician Hasse obtained the analog of the Riemann hypothesis for zeta function, a geometric analog, and that was a big thing because a lot of application. Eventually, Andre Weil extended this to the general geometric case, and he was hunted, being a Jew, he was hunted by the Germans. He was saved by the Americans just in time. He was already, they were going to shoot him, being a Jew. So the letter by Andre Weil noticed the analog of the Riemann hypothesis in this geometric setting. He proved it for in case of curves. So, and it should go in general, and the Riemann hypothesis remains as the biggest open problem in number theory, at least. So further progress, if standard joke. So at the end of a long, complicated, almost possible to understand mathematical lecture, are there any questions? If you don't know what to say, get up. Yes, yes, yes. Well, about the general case. So, anyway. Serre, the French mathematician Serre, a good friend of mine, that helped me at the beginning of my career to understand the connection of geometry and number theory. Again, showed that to study prime number, you must understand geometry, which looks strange, but it is so. Factorization is easy to do. It's not easy. Multiplication is easy, but factorization is very difficult. And so the difficulty of factorization has been used for encryption of secret messages. Well, you have to be careful. The method was described in some popular mathematical magazines, and some crooks decided to use that method to communicate their plans for things. Well, it turns out if the factors about the same size, it's very easy to find them. So they were unmasked, and their plans just got busted. So find a pair for a fairly close pair of numbers of two primes, fairly easy to find and to factor such a product. But the one factor, say, has 20 digits and the other one has 400 digits. Factoring it, even today's computer cannot do it in real time. So the zeta function is not an isolated object. They appear when you try to use geometry to study numbers, and the geometric analog has been understood very well now. The classical analog, the Riemann hypothesis, is still open, and I consider it the biggest open problem in number theory. So, about distribution of values and so on. So everything should follow Gaussian law. No, it's not so. And the behavior of the zeta function, statistics, well, at the beginning there is a part which is Gaussian. The other one use unitary group and symplectic ensemble. And in the study of zeta function, all three are fused together. And at the point they are fused together, it's just a total mess to understand. So the study probability theory, combinatorics, polynomials and functions of several variables. There are new areas of mathematics, and Swedish mathematics is extremely strong, and many young stars. So the combinatorics used to be just a side thing in mathematics, thanks to the Swedish young mathematician. I will not mention names, but they have really changed the way we look at probability theory in analysis. So this future mathematician is certainly very bright. Thank you.